Okay, so this is the third problem from the third set of lecture notes of David Tong. So in this one, I'm proving a bunch of gamma matrix identities. And so what I've done up here is just written a few things we'll need. One is the anti-commutation relation, the usual one. The definition of gamma 5. The definition of, p slash in this case, but any kind of thing with a slash through it just means contracting it with gamma mu. This S mu nu thing is 1/4 the commutator of the gamma matrices. And we're going to be doing a bunch of proofs that involve the trace. And one useful thing to know is that the trace, when I take the trace of a product of gamma matrices, or any kind of matrices, the trace, I can cyclically permute these matrices and it won't affect the value. So I can basically take this gamma and sigma and move it to the front and then, kind of slide everything else over, and then I can do it again. So all of these things are equal to each other. And that'll be an important thing to know for some of the proofs. So, and then another thing that we'll need is we need to know what the anti-commutator of gamma mu and gamma 5 is. So if I do this, I just write it out, basically using the definition of gamma 5. And essentially what will happen is, so I can write it as these two terms. And in this term, I can so gamma mu is always going to be either 0, 1, 2, or 3. And we know that basically we know from this relation, if mu is not equal to nu, then this will be 0. So our gamma matrices all anti-commute with each other. So since gamma mu will be either 0, 1, 2, or 3, let's say it's 0, I would commute it past gamma 0, because obviously it commutes with itself. Then I would anti-commute it 3 times past these. So I would pick up a minus sign. And I would get this term, but basically with a minus sign, and so they would cancel and I get 0. But I could also do, if it was gamma 1, then I would anti-commute it past this, commute it past this, and then anti-commute 2 more times. So no matter what I choose, I'm always anti-commuting 3 times. So I'm going to pick up a minus sign in this term. And so it'll look like this. And this is, then they cancel. So I get 0. So that tells me that gamma 5 anti-commutes with all of my gamma matrices, which will be important later. A few more things. So another thing this tells us is we can do the anti-commutator of, this is how we, prove that the square of gamma 0 is 1. I think I've used that in a few previous videos, but here we see why it's true. It's just because if gamma 0 here, we just get 2 times eta 0, 0, which is 1. So, so this tells us that gamma 0 squared is 1. And then we can do a similar thing with gamma I, and that will tell us, so eta II is minus 1. So the gamma I squared are all minus 1. Okay, so I'm going to do, the first thing I'll do is the fourth problem, which involves just proving that the square of gamma 5 is also 1, or the identity. So to do that, you just write out, using the definition of gamma 5, this thing. And so in this, it's just a matter of, I'm just going to anti-commute first the gamma 0 past all of these. So I'll be anti-commuting it 3 times. So I'll pick up a minus sign, and then I'll have a gamma 0 squared, which is 1. And then I'll have a minus I times I, so that goes away. So I end up with this. And then I just want to keep anti-commuting. I just anti-commute gamma 1 past. And so I anti-commute twice, so I don't get a minus sign. But then gamma 1 squared is minus 1. So I'm left with this. And here I just do one more anti-commutation. So anti-commute gamma 2 and gamma 3. So I get another minus sign. So I get positive gamma 2 squared times gamma 3 squared. Gamma 2 squared is minus 1. Gamma 3 squared is minus 1. So I get minus 1 times minus 1, which is 1. And so that's how you prove that gamma 5 squared is 1. The next one to do is proving that the trace of gamma mu, of any of our gamma mu's, is 0. And to do that, we're going to make use of this first thing we proved, which is that gamma 5 squared is 1. So I can freely insert it into this expression without changing its value. And then I know that gamma 5 anti-commutes with gamma mu, so I can anti-commute gamma 5 past gamma mu to get this and pick up a minus sign. And then I can use the, cyclic permutative property, whatever you want to call it, to just loop this gamma 5 back around. So, and then again, just gamma 5 squared is 1. So I end up proving that the trace of gamma mu is equal to minus the trace of gamma mu. And whenever you do that, that means the thing is 0, because the only thing that's equal to minus itself is 0. So then the next one will be proving that the trace of gamma mu and gamma nu is equal to 4 eta mu nu. So to do that, you just want to compute the trace of the anticommutator of gamma mu and gamma nu. So the trace of this, obviously, just plugging in the anticommutation relation, we get this. And then I'm taking the trace of this thing times the 4 by 4 identity, and the trace of the 4 by 4 identity is 4. So I get an 8 eta mu nu. And I can relate this to this expression. So this, if I expand and just write out the commutator, I get this. And I can, the trace is, I guess, distributive, kind of. So I can write it like this. And then I can use the cyclic property here to rearrange mu nu. So basically, the trace of this anticommutator of gamma mu and gamma nu is just twice the trace of gamma mu, gamma nu, which is what we were trying to find. So so I just get 2 times the trace of this is equal to this, which is what, after dividing by 2 is what we wanted to prove. So the third one works out in the exact same way as the first one. We just want to introduce, again, gamma 5 squared is 1. And whenever there's an odd number of gamma matrices, we're just going to anti-commute past all of them. And since we anti-commute an odd number of times, we pick up a minus sign. And then we can use the cyclic property of the trace to bring gamma 5 around. And we end up proving that the trace of this is equal to minus the trace of this, and hence it's 0. So the trace of gamma 5 is next. So this one, we can't introduce a gamma 5 squared because that won't do anything for us. But we know that gamma 0 squared is 1, so we can introduce that. And then we just do the exact same thing as this one. So again, anti-commute, we get a minus sign, permutate, it's equal to minus itself, so it's 0.